Okay. So I wanted to spend a little bit of time today quickly going over the homework because while I think this one is more straightforward, there are some catches, some little things in here. Okay. So question 1, right? That's just straight take the derivative and plug and chug, right? That should be no problem. No problem if you have a Wolfram Alpha premium account, right? You can even do the step by step. It can even show you the step by steps, right? So that's not a problem. Question 2 is in principle really straightforward, but there's a couple little things that can potentially catch people. So I want to just take a quick look at 2 and 3. I found from the theory, right, we know the steps, right? So we have to calculate the Gibbs free energy, the bulk Gibbs free energy, right? And then calculate the Gibbs free energy as a function of the radius, right? So we got to do our Gibbs-Thompson, calculate delta GR, right? And then from delta GR, we plug it into our Boltzmann distribution to get our cluster size, right? So that's just right out of the book. I found the easiest way to do this was in MATLAB. But however, I mean, that's just because I like doing computational stuff. You could do this in Excel just as trivially. You could even do it on paper or with a graphing calculator if you were so in pencil and paper, a graphing calculator if you were so inclined. All right. The thing that you have to check to keep in mind, and this is going to screw you up if you don't catch it, is if you look at the equation in your book, or in the reading and in the notes, right? The equation for delta GV, this is equation 4.3 in your reading. You have to remember this is L sub V. So this is the latent heat of fusion per unit volume, not per unit mole. And so if you plug in per unit mole, you have something that's on the order of 4 times 10 to the 4th, right? You got something that's, the latent heat is kilojoules per mole, right? Which means you're about 6 orders of magnitude off. So that means, of course, your equation's going to predict much less driving force for nucleation, and you're not going to have any nuclei, right? So I'm assuming here that we have 1 mole. I could have put in the easily just done the number of atoms in a kilogram, right? And had the number of nuclei per unit mass, or put in the number of atoms in a cubic meter, right? Use the density, and then I would have had number of nuclei per unit volume. I decided just to assume 1 mole and see what we have and see how it goes out. Okay, so I assumed some kind of small undercooling, right? And you just sort of flop through here. Okay, and so here's the cluster size. Here's the number of clusters, right? If I have a really, really small cluster of like 1 atom or so, I have 10 to the 23, 6.02 times 10 to the 23. And this really falls, and at R star, I'm predicted to have 10 to the minus 20 something clusters, right? So essentially 0, right? If I have, right, that means I essentially would need a mole of moles to find one nucleus, right? So that just points out how little driving force you actually have for nucleation very close to the melting point, right? If we do this now at an undercooling of 0.9 melting, we get a graph. Of course, it's got the same sigmoidal shape, but look at the scale now. Of course, I've plotted both of these on a log scale. You can do it on a linear scale, but you see out at R star, the minimum, the asymptote that it goes to is still around, this is 10 to the 23rd, right? And if we look at the actual values, the number of clusters, right, we still have about 2 times 10 to the 23rd clusters of size R star, right? And our R star is tiny, right? Our R star is, right, super small. So, so yeah, so then, like I said, the only real trick here is make sure that you've got your specific heat per unit volume. The surface energies are in your are not in the reading, but you can find those in the book in chapter 3. They're also in the Turnbull reading that I assigned. Actually, the book just takes the chart from the Turnbull papers and republishes it. It's table 3.4 in the Porter and Easterling book, right? So you'll remember that picture from the notes. But it's the surface energies are all right there. So question 3 is really just a version of the same thing, except now we're doing the nucleation rate. Let's see, where is my, okay. Picture of a Hansen cab, what's that from? Okay, so I said estimate the homogeneous nucleation rate for pure copper at a couple of different undercoolings. Since I already had it typed up, essentially I could just cut and paste the previous put in the parameters for copper. The equation in the book, the form of it is the nucleation rate per unit volume. So here I've substituted in the number of atoms per cubic meter, and did the same thing. And now essentially just plotting the nucleation rate as a function of, we'll plot this on a linear scale as a function of undercooling.
You don't need to plot this one, do you? You just need to find the 3 values.
You just need, I just ask you to find the 3 values, but since I already had it written for the previous one, it was faster just to cut and paste. And I thought I would just show it to you guys real fast here. So what you get, if I plot the nucleation rate on a linear scale, right, you can see that somewhere right around 120, undercooling of 120 Kelvin, right, we get this essentially step function in the nucleation rate, right? So if we look at the rate as a function of time, of course, at 0 undercooling, we get not a number, right? Because we would need an infinite amount of time. But if we go to 120, right, we've got about 30,000, 35,000 nuclei per second. If we go to a smaller undercooling, right, let's say 100 degrees, right, we end up with a nucleation rate of 10 to the minus 7 per second, right? So that means we need to wait about 10 million seconds for a nuclei to form. If we go just a little further back, we drop really fast. So at, say, 75-degree undercooling, right, we'd have to wait longer than the age of the universe, right? The age of the universe is what, 10 to the 18 seconds, right? So essentially, the nucleation won't ever occur at won't ever occur homogeneously, I should say, at these smaller undercoolings, right? So working through this just sort of really shows you how much of a step function this is and how the statistics of large numbers works out, right? Okay, so question 4. This one, I'm making a decision. I'm going to make this question extra credit. Not because it's conceptually very difficult, but I worked it out last night. The long way, and I did this as a student, and that was the last time I worked this out. I remember having this exact question. I actually did it twice. Once was, as an undergrad in this kinetics class, and then once was a grad student in the fundamentals of ceramics as an exam question, and I don't remember it being as fiddly with the trigonometry as it is, right? So question 4, I'm going to post a revision. This question is going to be extra credit, right? But the idea behind it is really simple, right? So what you can do is you calculate if we just take this expression, right? V star here is the volume of a spherical nuclei with a radius r star, right? So that's really easy to plug in for homogeneous nucleation. And you'll see that when you plug this in, you get 16 pi gamma cubed over 3 delta GV, right? Which is what you expect. For heterogeneous nucleation, it's a little tricky because V star isn't a sphere anymore, right? What is V star? I apologize for just holding up the picture, but it's easier, right? So here's then going back in the notes. So here's our image for heterogeneous nucleation. So what you have to do then is calculate the volume of the spherical cap as a function of the contact angle, right? And that's where the trig gets really fiddly. So that's figure 4.7 in the book. I've got my paper copy is the older one. This is on page 192, but it's in the assigned reading, right? It's also in the notes. as well, right? And so if you're really good with trig identities, it's not that bad, but most of us are not. And it took me, it was a lot more, it was a lot more involved than I remember. So, you know, I'm just going to make this extra credit for everybody, right? Question 5 and 6. There's, you know, these are just sort of more conceptual, right? You don't actually need highly detailed numbers for these, right? You can just look up approximate values, right? If you just Google right, use Google as your friend here to find these interfacial energies. Page 196 in newer editions. Thank you. Right, but this is a pretty, this should be pretty easy. I kind of gave it as a bonus, you know, because I made this 20 points. And it's worth, because I thought this was something that I thought was important, but not too difficult, and everyone can get some points here. Also, question 6 is, again, just purely a conceptual question, right? And just think about what happens with the critical nucleus size for the atomically flat interface for lateral growth as the temperature, as the undercooling gets larger and larger, right? So hopefully that's helpful. I think I'm going to keep, there'll be another homework assignment posted this weekend, right? And that'll be the last homework of material that's going to be on the exam. Right. 3 is due, I don't recall exactly which day. It's either, I think it's due Thursday, right? Next Friday? Okay, next Friday. Right, and then the homework 4 will be due a week after that. The solutions to 1 and 2 will be posted on Carmen over this weekend, and we'll get those back to you graded fairly quickly. Okay, so today I want to hit this dendritic solidification. This is a topic I want you all to think about conceptually more than quantitatively. You'll notice there's fewer equations in this slide, or what equations there are, there's fewer derivations, right? I just sort of present some things. Right, so that's kind of a clue. I want you to think about it and get the main ideas, right? So this is if we have a, right? So we had, we talked about how in the previous lecture, when we're solidifying a alloy, the solute is rejected by the new solid into the liquid, right? So the liquid becomes more and more concentrated, right? So what happens to the melting point as the liquid becomes more concentrated? Right? The liquidus line essentially goes down. Right? So the melting point gets lower. Okay? Which means that right? So this is where the people get confused, because there's a tendency to get the melting point and the undercooling confused here, right? So let's just think about this conceptually. The melting point is lower directly in front of the right? The melting point directly in front of the interface has been depressed. So that means if we keep the temperature constant, let's just pretend for a second that the temperature of the liquid is completely uniform. But now I have this solute pile up in front of my interface. So what does this imply about my undercooling as I move away from this interface? So close to the interface where I have lots of solute, my melting point is lower. So that means my undercooling is lower. Out here, I have a higher undercooling than out here, than here. So what does that mean about my growth rate? Right? When we talked about growth, we said it's going to be proportional on the undercooling, and the greater the undercooling, the greater the growth rate. So that means if I grow a little protrusion on this interface, it's now going to grow into a region with a greater undercooling, and it's going to become unstable. Right? So we're going to work through that, but that's kind of the high-level overview of why we get these dendritic solidifications, right? Okay. Did someone have a question?
I have a question.
Yeah, go ahead.
What do you mean unstable?
So it's not going to stay planar. It's going to grow as a dendrite, right? So when we had a pure solute, we talked about the thermal dendrites that formed when we had a heat flow that was going through the liquid, right? When we had a negative thermal gradient in the liquid, we had accelerated heat conduction around the dendrite as it grew out, right? So a small protrusion on the interface grew into a long dendrite, right? So that type of instability leads to thermal dendrites forming. We also, today we're going to look at how the solute pileup leads to a similar instability and gives us dendritic growth in the same way, right? Okay. So if we review quickly what we talked about on Wednesday, where we assume we have no diffusion in the solid and diffusional mixing in the liquid. right? We're going to reject solute from the growing solid into the liquid. The liquid, the concentration of the solute in the liquid in front of the growing interface is going to be higher than in the rest of the bulk liquid. And the width of this is going to be dependent on how fast the interface is growing and how fast it can diffuse away, right? So the width of this region is this characteristic with the diffusivity coefficient in the liquid divided by the velocity of the interface, right? And the maximum point of this is going to be our alloy composition divided by kappa, our partition coefficient, right? Okay. Right, so this is just the review, the situation that we are looking at, right? So this is one of those really, really important figures to understand sort of conceptually, okay? So let's pretend we have a temperature gradient in the liquid, but now we have a positive temperature gradient, right? So which way is heat flowing? Are we flowing through the liquid or flowing through the solid? Right?
In this bottom image,
Yeah.
based on the gradient, it appears the heat is flowing through the liquid.
Well, okay, so so the temperature of the liquid is higher out here than it is at the interface.
Oh, whoops.
Right?
Sorry, it's
Yeah.
a little confusing.
No, I know.
Heat flows
This picture is a little confusing. That's why we're walking through it step by step.
Basic chemistry rule: heat flows from high to low. So since the temperature is high to the liquid, it should almost always flow through the solid, unless there's something. Unless you're cooling the liquid, it will flow from the liquid to the solid.
So we're gonna flow through the liquid to solid unless someone has found a way to violate the second law.
Yeah.
Right. And reverse the direction of entropy. Right. We're going to flow, in this case, from the liquid to the solid. Right. So if this were a pure substance, this would be a planar growth, a stable planar growth front. Right. Anytime we made a little protrusion on the interface, it would slow down because there'd be less effective heat transfer, right? We would make the gradient in the liquid steeper and the gradient in the solid would be shallower. So there would be less heat flowing through the solid at that region, and the rest of the interface would catch up, okay? But because we're changing the concentration as well, the composition of our liquid, we can actually get an unstable interface even with heat flowing through the solid, right? So everywhere, right, at the interface, the temperature has to be given by our equilibrium temperature, right? Right. So at the interface, local equilibrium still has to hold. So we're going to be freezing at the temperature that's given by the solidus liquidus line. Right? So in this case, if we're at composition X naught, our solid has composition, we're at the interface, we're at temperature T3. Our solid is at composition X naught, right? And our liquid directly in front of the interface has to be at composition X naught by K, right? So what's important to realize here is our composition concentration decreases as we go further out, right? So that means, what is the equilibrium temperature, the equilibrium solidification temperature as we go out, right? That's not the physical temperature of the liquid. It's the equilibrium solidification temperature. And this T sub E is given by the liquidus line. So as we go out, our equilibrium solidification temperature gets higher and higher and higher until when our concentration gradient goes away and we're back at our liquid composition of X naught out here. If we have a liquid composition of X naught, our equilibrium solidification temperature is given by T1, which is much higher than T3. Right? So this line, this curved line, represents the temperature that the liquid wants to freeze at for its given composition. Right? So that means if our temperature gradient is less than this, right? If this is the temperature of our liquid, right? Anywhere that the temperature of our liquid is lower than this curve, we're effectively supercooled based on the local concentration, right? And because this is only an effect of the concentration or the chemical effects, right? This is called compositional supercooling, right? Which basically just says, if I suddenly moved my solidification front into a region of lower composition at the concentration that it is, I'm increasing my delta T, and my growth velocity is going to get much faster. Okay? Okay, so I want everyone to pause here, because this is a concept that always throws people. Okay? I've sat in candidacy exams for PhD students, and a question where this came up totally sunk them, right? And they ended up failing the exam, more than one person, right? Because they thought they understood what was going on, and when they were forced to actually draw this out and explain it, got themselves all tied up in knots, right? So, and ostensibly those students, being PhD candidates or people trying to become PhD candidates in material science, have seen this on several occasions. You're seeing it for the first time. So I fully expect confusion from you right now. Okay? So someone throw out questions or start this discussion, so maybe I can try and explain it in a different way or look at it in a different way. Okay, well, let me ask the question a slightly different way. Does anyone feel comfortable trying to explain what's going on?
Someone besides me, please.
Someone brave enough besides Kevin. Someone who's not afraid to show that they don't know something, that they're a little confused. Okay, so Aiden, I'll get to the definition of the critical gradient in just a second. I didn't throw that in there because that's just an extra layer, an extra thing to get confused about. Right? So so Kevin's question, X sub L is the composition of the liquid. Right, in front of this growing interface. Okay, so who's going to be my brave soul? I don't want to have to pick on somebody. I could be, okay. I'll be mean and pick Aiden because since I'm nominally his research advisor at the moment, he has less less leverage to say no. So I'm sorry, Aiden, but are you there? Okay, so let's just start right from the beginning, right? What's the origin of the composition gradient in the liquid? Okay, solute pile up at the interface. Can you make your is your mic work? It'd be a little easier to talk to you directly rather than through chat. Does the chat show up in the recordings? I didn't look.
I believe it does show up in the recordings, or at one point you had a transcript that you uploaded.
Yes, it does show up in the recordings.
Okay, cool.
Yeah.
Or at least it shows up in the cloud recordings. I don't know if it shows up in the local ones.
Okay. Okay, so that's good. So we've got the chat on the screen at least. Okay, so are you there, Aiden?
Yes.
Okay, so the origin of this composition gradient.
Solute piles up at the interface.
Solute piles up at the interface, good. Okay, so what happens to the equilibrium melting temperature as you increase your concentration?
It decreases.
It decreases, right? If I have a constant temperature, right, of my liquid right in front of this interface, right? I know that's not a physical situation, but let's just pretend that we have a constant temperature in the liquid and then a step function at the interface, right? And a temperature of the solid, right? A temperature of the solid, right? It's not, there's no way we can actually make that work, but let's just pretend we have it for a second. What does that mean about the undercooling as we move out? Right? If the melting temperature is lower here than it is out here, what happens to our undercooling?
I believe there's a greater driving force to solidify closer to the interface.
It's the exact opposite. Closer to the interface, we have a lower undercooling than farther away from the interface. Right?
You say the liquid was a constant temperature.
If we assume the liquid's at a constant temperature and the melting point of the liquid is lower here than it is out here, right? Our melting point out here is higher than back here, right? So that means our undercooling, the difference between our actual temperature and the melting temperature, is small here, but large here. Right? Does that make sense?
Yes, I was thinking of a thermal gradient as well. I didn't
Exactly.
think of the constant temperature part.
Yeah, exactly. But this is something that everyone sort of trips up on, right? So we're going to review this again on Monday and then the homework and all that, right? So nobody panic. Right. So now we've got a undercooling that varies with position, right? And so we have a low undercooling here and a high undercooling here. So what's going to happen if I get a tiny little bit of a protrusion on this interface?
It
Right?
should expand out as a
It's gonna-
dendrite because the driving force is higher on the right.
The driving force gets higher and higher the further this dendrite grows out. So its growth velocity is going to get faster the farther and farther it grows out. Right? So now we add the issue of this thermal gradient in here, right? So if we had no composition gradient, I've got heat flow going through the solid, so this should be stable. But now that I've added a composition gradient, I've got a essentially a battle between my thermal gradient that wants to keep the interface stable and my composition gradient that wants to make it unstable, right? And if my thermal gradient is steep enough, then it will be steeper, right? And that's where this critical gradient comes in, right? The critical gradient is the temperature gradient that keeps me above this compositional supercooling region at all times, right? And so if my thermal gradient is really steep, meaning I have really good heat flow, I'm sucking heat out of this really, really, really well, then I can keep a planar solidification front. If I can't get the heat out fast enough, then I'm going to get dendritic growth. Right? Okay. What is that critical gradient? Right? Well, the critical gradient is going to depend on how fast the solute's piling up, or that width of, right, this width, critical width here, or this characteristic width given by D over V, right? And the difference between these two temperatures, right? So essentially, I need to have a thermal gradient that's greater from T3 minus T1, this temperature range, over this characteristic width. So if my slope of that is greater, then I'm going to remain stable. If my slope of that is less, I'm going to have dendritic growth.
Good question.
Yeah.
How do you know where to find? Go back to that image, please.
Yeah.
So you find the width you need at the between the XO and the T1, right?
Yeah. Right. So XO is composition and T1 is temperature, right? So
Yes.
I think I know what you're asking, but what can you rephrase your question a little bit so that it's consistent?
My question is, how do you know that exact value? I mean, like, Is it just the XL minus XS or?
XL minus XS right, yeah. Right, so your partition coefficient. So if we're in, once we're in the steady state regime and our composition gradient has gone up, we know that T3 is going to be given by our solidus line, right? And then we come across our T3 to our liquidus line, and we know that's our composition up here, right? And if we know the temperature gradients, the actual temperature gradients, we can calculate our velocity. It's a little tricky because the diffusivity also depends on temperature, right? This is why I there's not as much quantitative stuff here. I want you to think about this philosophically. Right. So from, I guess sort of what you're asking is, from a theoretical point of view, everything you have everything you need. Actually measuring this is really impossible because there's a lot of things that are all interconnected, right? So experimentally, doing experiments with this is not at all sort of straightforward. Does that answer your question, Kevin?
Yes.
Okay. The main thing I really want everyone to be able to explain what the origin of this compositional supercooling is. Right? If you can do that and apply a couple simple calculations, assuming you know all the parameters here, then I'm over the moon. Okay? So I know this is a confusing topic. It's a confusing topic for everybody. You're not alone. Okay? And it's one of those things that once it clicks, you're like, oh, that's it. Right? So what I want to do is try and make it click. Right? So we're going to quickly, we're going to review this again on Friday. Right? But what happens is, right, we get a small little protrusion that forms, right? And it doesn't quite grow into dendrites the same way as the pure thermal case, because I'm now rejecting solute in 3 directions, which means I'm going to increase the concentration locally here faster, right? Which is going to retard the growth right near the root of this protrusion. So I actually get a recess that forms, right? Which nucleates another little protrusion, right? So we get, what ends up getting is the series of stable fingers that grow parallel to the direction of heat flow, right? And this is solidification of carbon tetraboride in cross section, right? And you see these beautiful finger-like protrusions that form. This is a lead tin alloy, very much like solder, or what solder used to be before they removed the lead, in cross section. Okay, we'll talk more about the recesses on Monday. And Joel's question, can you use that to manipulate the grain orientation? Not really, no, because these all are growing from the same solid. So all of these cells, these growth cells, have the same crystal orientation, right? So Wei, if the thermal gradient is deeper, it's going to develop a dendrite. Yes. yes, it is most definitely going to form dendrites, right? So as your temperature gradient gets, the thermal gradient becomes even steeper, these cells form secondary dendrite arms, right? And you get a transition from cellular growth to dendritic growth. That transition is not really still well understood. It's an active area of research. Okay, so Nathan's question, could you please repeat if the undercooling is larger at the interface or at the end of the sample? Okay, so your undercooling is your equilibrium melting temperature is increasing as you go out this way, right? So if this were a constant, if there was a constant temperature, so if this T sub L line was flat, exactly at the interface we have no undercooling. As we move away, the undercooling would be the difference between this TE line and T3, right? So our undercooling is greater the farther away from this interface that we are.
Okay, thank you.
And however, though, when you have an actual thermal gradient, your undercooling starts at 0, goes through a maxima, and then becomes 0 again. Right?
Can you show what undercooling would be at a minimum?
The undercooling's at a minimum here. Right?
So going along that line would lead to dendritic formation then?
If T sub L were if T sub L, if this were at a max, if you would maximize this, right? So I guess I was a little loose with my words for Wei's question. So the shallower this the gradient into the liquid is, right, you're gonna get more dendrites. Dendrite, right? So the greater your undercooling gradient, the more likely you are to transition from dendrite to solid. Right. Okay, so we're going to wrap it up there. Monday, I'm going to briefly review this. So when the temperature hits the critical gradient, it is definitely stable solidification, yes. Okay. Think about this over the weekend. We're going to review this on Monday again. And talk about how we use this alloy solidification with zone refining to make really pure materials such as semiconductors, silicon and germanium for functional materials. Right? Okay. Have a good weekend, everybody. And enjoy yourself in case the world ends soon. Okay, bye.